Brookhuis Applied Data Intelligence makes a set of e-learning videos on clean rooms. This video will be on air cleanliness. Air cleanliness can be measured with a light scattering airborne particle counter, but for large particles we can use a particle deposition monitor. I will explain a little bit about the different type of measurements and the relation to the ISO standards. Particles in air. When we look in the outside air, there are many particles, especially many small particles. These particles, they arise from biological processes, from fauna, flora, and from geological processes like erosion, volcanic activities, and industrial activities, traffic, factories, and so on. So all these sources make the concentration of particles in the outside air very high. We're talking about billions of particles per cubic meter. A clean room is a separate space, a box in a box. And we supply this box, this room, with clean filtered air. So that inside the clean room, the air cleanliness is very good. We have a very low particle concentration. When the clean room is in use, people come inside, equipment is running, then those are the sources of particles and they will change the concentration of particles in the air, but they will also change the particle size distribution. In the outside air, many measurements are taken to learn more about fine particles. In fact, the mass of the particles smaller than a particular size is measured, like particles smaller than 10 micrometers, particles smaller than 2.5 micrometers, or particles smaller than 1 micrometers. This is expressed in PM1, PM2.5, and PM10. Of these particles, the mass of the total number of particles is measured and expressed. In a clean room, we count particles. So we count the number of particles larger than a particular size per cubic meter or per liter of air. When we do that with a light scattering airborne particle counter, we look in fact at the effect of particles on a light sensor, and because of that we talk about equivalent particle sizes, equivalent diameters. Large particles, it's easier to collect them on a filter or on a surface and look at them under a microscope. But then you see the particle and you cannot determine an equivalent diameter anymore. So then we just take the largest size of a particle, or in fact the smallest circle which you can draw around a particle. On my presentations, I write a capital D if I talk about larger particle size, and I use a small d if I talk about equivalent diameters. The most common instrument to count particles in air is a light scattering airborne particle counter. There are different types, and the difference is in the sample volume. The small ones take 0.1 cubic foot per minute. Then you have the most popular one, 1 cubic foot per minute, and a new group are the counters of 50 liters or 100 liters per minute. The higher the volume you can take, the lower the concentrations you can use this instrument for. A light scattering particle counter looks at the scattered light by a particle passing a laser beam, and that gives an electrical sensor signal, which is compared with the signal of non-spherical particles. So that's why we talk about equivalent diameters. Other ways of measuring airborne particles is by an impactor, where the air is sucked over different surfaces with different speeds, and depending on the speed, particles stay in the airflow or deposit on sieves or witness plates, which can be inspected later on under a microscope. You can also draw your air sample directly through a filter and then examine the filter under a microscope. In that case, you look at the particles and you see the particles, so the diameters you're looking at are the real diameters. So there's a little bit of a difference when you compare it with a light scattering airborne particle counter. When we look at a clean room, when the clean room is used, people come into the clean room, equipment is running, and particles are generated or distributed throughout the environment. The clean room is ventilated with filtered air, and as long as particles are airborne, they can be removed out of the clean room by airflow. But larger particles, they will deposit by sedimentation or impaction out of the airflow onto surfaces. And the larger the particles, the more likely it is that it is not removed by airflow. You see a diagram where I have two graphs. One graph shows you the efficiency of particle removal. So when you look at 5 micrometers, it is very high, somewhere between 95% and 100%. But then when you go to larger particle sizes, you see it's dropping down. When particles are not removed by airflow, they are automatically deposited onto surfaces, which shows the other curve. In the middle, at 50%, you have a kind of midpoint where 50% of the particles is removed by airflow and 50% will be deposited. When you increase the airflow, the air supply, these curves will just move a little bit to the larger particle size. So in this example, we have 20 air changes. If you double the number of air changes, the midpoint will move from 15 micrometers towards 25 micrometers. But whatever system you have, whatever air volume you have, large particles will hardly be removed from the clean room by airflow, and they will deposit on surfaces. So because of this phenomenon, it's also very difficult to count these particles with airborne particle counter. So therefore, for measuring the concentration of larger particles in air, it's easier to use a particle deposition monitor, because a particle deposition monitor has a larger cross-section of your airflow. It can measure over a longer time or sequential when you do real-time measurements, and therefore they are able to measure the low concentration of these larger particles. The air cleanliness is expressed by the number of particles larger or equal a specific size. When you want to classify a clean room, we use a classification table which is in the standard for clean room classification ISO 14644 Part 1. The latest one is from 2015. When you classify a clean room, you choose one particle size and you look at the limit for each clean room class. Let's say ISO 6, then you look at the limit values of ISO 6 for the different particle sizes, but you only measure it for one, maybe two particle sizes. When you have a clean room at rest, it's often good to measure the concentration for particles of 0.5 micrometer. But when a clean room is in use, in operation, it's much more useful to look to particles larger than 5 micrometers or to both particle sizes. So when you classify a clean room, it's important you always look at the state that the clean room is in. If the clean room is at rest, the particle size distribution is often more or less the same as what you find in the distribution in the classification table. So the number of particles is more or less proportional to the square of the particle size. As soon as the clean room comes into operation, particle sources like people and equipment come in, more larger particles come into the air and automatically the particle size distribution is changing. It's increasing by 1 or 2 decades, and it's changing in such a way that the number of particles become proportional to the particle size. That's also the reason why in an operational state you get a less good cleanroom class for 5 micrometers than for half a micrometer, and therefore it's better to look at 5 micrometers because it gives you more realistic value for your cleanroom in relation to the products you are making. So because you see in the graph that when you go from at rest to operation, that the slope of the curve is changing, that shows you also why there are more larger particles and why it's important to measure the larger particles using a particle deposition rate monitoring system. Particle counters are also used to look at air cleanliness at critical locations for monitoring, because a classification is something you do once a year, maybe 2 times a year. It's just one moment looking for the worst place in your clean room. When you're monitoring, you do regular measurements or even real-time measurements at a critical location, and you look at trends, and this information is important for the contamination control in respect to your product. So when you want to use a particle counter or a particle deposition monitor for monitoring purposes, you always start with a risk assessment. When is my product most at risk? What is my critical particle size? What is the critical location? And that's the place where you are going to put your monitor. Depending on how much changes you can expect, you can set your frequency of monitoring. This is all described in ISO 14644 Part 2, also from 2015. When you use a real-time monitoring instrument, it's also very interesting to show the data directly to personnel, because they can see the impact of actions they do inside the clean room. The measurement methods for air cleanliness are described in the same standard as the clean room classification. Other measurement methods are described in 14644 Part 3. Also, the method of measuring particle deposition is described in 14644-3. In the version of 2005, particle deposition is only measured by looking at the change of mass onto a witness surface or by the area coverage. In the new version, which will come out this year, also the number of particles depositing on a witness surface is included. Soon there will also be a new ISO standard on particle deposition rate applications, which will be 14644 Part 17, and that one will be ready by next year, because the draft will be voted on in the course of this year. So when we look at particle deposition monitoring, we need to look at 2 standards, Part 3, the new one, and Part 17. So when we look at ISO 14644 Part 17, there is also a table which shows you the different levels of particle deposition rates. And this is set in such a way that we look at the deposition of particles larger or equal 10 micrometers per square meter per hour. So you can have different levels of, let's say, 1 particle larger than 10 micrometers per square meter per hour, which is very low, up to 1 million particles larger than 10 micrometers per square meter per hour. And in the table you can also see the related values for smaller particles and for larger particles up to 500 micrometers. The particle deposition rate is in fact the product of the particle concentration in the air times the deposition velocity. So by measuring particle deposition rate, you can calculate the particle concentration in the air by dividing by cumulative deposition velocities, which you can find in literature or which you could measure through an experiment. Particle deposition rate is an important parameter to determine the risk of product contamination, and when you multiply it by the time of exposure, it also shows you how fast surfaces get contaminated in a clean room. Thank you for your attention. Brookhuis Applied Data Intelligence makes a series of videos to educate you on various aspects of clean room technology, contamination control. On our website you can also find more in-depth papers on various subjects. So I'll invite you to go to the next video.